Greetings, everybody that's joined us for this webinar. I'd really like to thank everybody for taking some time out to learn about Mechanical APDL, elements, contacts, and solver updates in Ansys 2020 R1. It looks like we've got a full house. There's 43 people logged in. So I will go ahead and get started. My name is Eric Miller, and I'm one of the owners here at PADT, one of the founders as well. And I'm a longtime Ansys user, so they've asked me to do this presentation as the rest of our team is dealing with some other stuff. As you can imagine, we're a little busy right now. I will state before we get started, we're all working from home on the Ansys side of things, but we're fully operational. Everything is up and running, and all of our capabilities exist as you would expect. So if you are one of our customers and need support, please do give us a call or send us an email. It's actually better. So let's go ahead and get started. So we're PADT. It's been a while since I've done one of these things, so I'm getting and I haven't done one at home before, so I'm getting my screens all together. I'm looking at the right screen now. We're Phoenix Analysis and Design Technologies, and we make innovation work. We were founded in 1994 by 4 turbo machinery engineers. I was one of those. And we're based in Tempe, Arizona, with offices across the Southwest, all the way from Texas to California. And we're about 85 employees. And we do 3 things in 3 different ways. We sell, support, and service numerical simulation tools, Ansys being the primary one, product development, as well as 3D printing. And you probably all know us for numerical simulation, sales, support, and services, because you're on an Ansys call. I'm making that assumption. In the numerical simulation area, we are an Ansys Elite channel partner. We sell all the way from Texas to the full state of California. And we also sell another product called FlowNext, which is a 1D flow tool, and we help people find HPC compute solutions in the cloud. Our support team is frontline product technical support for the products we sell, as well as training and mentoring. And then in the simulation side, the services side of things, we basically can do any kind of simulation that Ansys uses. And now that LS Dyna is part of the Ansys family, we can very proudly also do much more robust and capable in the LS Dyna area. So we do have a full services group as well. From a sales standpoint, like I mentioned, I have to get the updated slide to the team because we now sell up in this part of California as well. And actually, you got to see it over here, I think, to see it. And what's different about us is we're very customer focused. We understand how customers use Ansys because we use it in our own services business. We're technically very strong. I think if you ask somebody what's the first thing that pops in their mind about PADT, it's our technical strength. We know the tools, we know the theory, we know the process that they apply to, and we are full physics. So although we're talking about Mechanical APDL here today, we do HFSS, we do Maxwell, we do Fluent, we do CFX, we do some of the newer tools as well, Grant, et cetera. And we've been doing this for a long time. We have relationships with customers over 20 years, and we're all about long-term customer success. And with what's going on with the COVID-19 and everything, this is really coming to play where we're really helping our customers get set up and working at home and making sure that they get the support they need so they can continue to do their job in what is unusual circumstances. So that's working quite well. I also want to talk about Ansys Cloud. So this is a new capability that's been around, it's a little while now, but the ability to just do a one-click and solve in the cloud. It's web-based 3D post-processing. It's highly optimized for the Ansys thing. So Ansys has been working with Microsoft to get this to work for some time. And when we say it's highly optimized for Ansys solvers, it really is. I mean, this is the Ansys support and services team working closely with Azure to get some good turnaround times. And it's a single vendor solution. If you buy, you can get cloud. We have cloud solutions that we can help provide as well. But if you get the Ansys cloud, you're basically just getting things from Ansys or your channel partners. So it's a lot easier. The slogan is really HPC as easy as it should be. There's a pop-up window on the bottom of the screen. Thank you for pointing that out. I have moved it. Thank you for letting me know. Someone said the sound stopped. Ted, is the sound still going for you? We're getting questions from the audience. So our theme here is that HPC is as easy as it should be. And it basically allows you to burst to the cloud. You can run larger, more complex models if you don't have the hardware, or if you want to run multiple models, you can run them as well. You can also evaluate design variations, and it's a really powerful tool, and we really recommend you get a 30-day trial. We can talk about how wonderful it is, or you can just try it. So reach out to us if we're your provider or whoever you get your Ansys from, or go to ansys.com/cloud-trial and give it a shot. So I'm going to assume you guys can hear me. Okay, so people can hear me. I guess sometimes one thing we've learned is that our internet bandwidth, when a good third of the country goes home to work, it works, but it's taxed. So things do come and go. So let's talk about mechanical APDL, linear dynamics. We'll start there. This is my favorite area for improvement. Those of you on the call probably already know this, but let me back up and kind of explain what is MAPDL. It is the original code, Ansys, that John Swanson wrote. It's the original software. There's still pieces of it that he wrote, although it's been rewritten and improved through the years. And it was a multi-physics, finite element, monolithic piece of software that did everything: fluids, electromagnetics, acoustics, it's all in there. And then as Ansys has grown and acquired new tools, and the user interface and the geometry engine built into what's now MAPDL had become kind of obsolete, the solver was still very viable. And so what we've done is we've moved, most of the post-processing is done in mechanical now, and APDL, mechanical APDL, is what's run when you hit the solve button. But you can still get into the tool. Hopefully you're on this call because you know that, and you can run these things without mechanical using the older interface as well. And these, hopefully most of these things we're going to talk about will be exposed in mechanical at some point. Yes, and as someone pointed out, it's often referred to as classic. So the objective here, the first thing we're going to talk about is component mode synthesis. So component mode synthesis is a way to model very large structures by creating reduced order models of the stiffness and mass matrix and solving them using some fancy math to get pretty accurate results, even though you're not only modeling a portion of the matrix. You're solving a portion of the matrix, a simplified version. And we use these things in it called master nodes. These are the nodes that are exposed in the matrix. These are the ones that are kind of on that you're solving for, right? So we want to create better convergence and improve performance when the master nodes are defined at locations other than the interfaces. So if you imagine you've got a beam, and that beam is attached to two mounts on either end, and you're substructuring that beam, you want to know what the deflection is at several points along the beam. Well, it can get kind of inefficient when you do that. So we've got a better way to do that. So we can go ahead and turn on, when we're using the free option for component mode synthesis, and turn support equals on in the M command, then they create these pseudo constraints are specified on the master nodes so that it enforces constraints during the mode extraction and the generation pass. So it kind of tricks it into saying, hey, I really am constraining it here. You're not. But hey, pretend that I am, so that the extraction, everything goes a lot better. So there's the command right there. It's also called the mixed method. And I will click here. Oops, I went too far. I won't go into the equations here, but they're available for you guys to look at in the manuals as well. So basically what we do is we generally define these master degrees of freedom, and we're going to call them M1 and M2. In the fixed method, all the degrees of freedom, M1 and M2, are fixed. In the free and RFFB methods, all the master degrees of freedom are unconstrained. So both M and M1 are unconstrained, right? And then in the free method with support on, we're basically saying that degree of freedom M1s are constrained and M2 are unconstrained. So we've got two sets in there, and that's what allows us to do what we need to do. So pretty nice. And here's an example. The full analysis is on the right side. The CMS use pass is on the left side. And you can see that what we've defined is nodes along kind of the middle here that we're getting results for. And so we got M1 all, and then turn them on. And M2 are the traditional ones that we would normally get. And we get almost the same answer, right? It's pretty dang close. So definitely give that a shot. It should run faster and give you good results. Another tool that we use a lot, when we're comparing different models, and that would have been a good place to use it, is the RSTMAC command, and it allows you to look at two different solutions and combine them. So we've got a new option called DOF, and you can specify 1 degree of freedom or a combination of degree of freedoms that you want to compare, and it supports the non-structural degrees of freedom. So if you're doing a coupled field analysis, like you've got pressure and voltage or magnetism or temperature, you can go ahead and put those in there and get results back for those. And the support node match, it does support the node matching based on node number. So if you're morphing the mesh or translating the mesh, rotating it, as long as the numbers stay the same, it'll work just fine. So here's an example of it. They're using the verification model number 282, and they're doing two different meshes of a piston fluid using the fluid 30, and they're looking at using the command, the MAC opt command. They're looking at how the pressure varies between the two substeps, and they're seeing that right here. So good comparison. So that's it for those capabilities. Now let's talk about the dynamics. Let's talk about the elements. So here's the list of the new features. I always hate reading this list because then you end up talking about them, so we'll just jump right into it. To me, this is the coolest one because it's just, if you look at the animation, hopefully that's coming through well on the video, it's pretty dang cool. You can model a cable using a beam, basically. You specify the two endpoints in an orientation node. So it's a 3-node element. It allows you to do extremely slender cable structures, right? It's very efficient because it only has translational degree of freedoms. It doesn't have other ones. And you can have the mixed displacement force formulation to get, they refer to as superb solution accuracy and robustness. I think it was Alex told me that he ran this, and it really does work well. It really is robust. And I don't know if he'd use the word superb, but it's really, really good. And there's a lot of applications. We can use this for offshore oil, civil engineering, and mechanical machines. The winding one up here is just amazing to me that we can model that now in Mechanical APDL. It's pretty impressive that it does that. And then this twisty guy, so it's obviously doing contact with itself as well, and a basic pulley. So a lot of things that we've never really tried to do in the past, we can now do with these cable 280 elements. So it's pretty neat that they added that. Oops, I'm clicking on the video, so it's not changing. So inverse analysis is what we used to call back in the day hot to cold. So the idea of an inverse analysis is I want to find out what if this is the final shape I want to find out what an initial shape needs to be so that when I apply my loads and boundary conditions, it distorts into my goal shape. And they've added, it's been around for a little while, and they've added some new capabilities. It supports the solid 185 B-bar formulation, as well as the 186, 187, and 185 B-bar, and with mixed UP. And it does support, this is probably the most important part, large deformation with incompressibility for the biomedical applications. So, the example that they're given below is if they take a balloon basically and stick it inside aortic lumen under some pressure there, blood pressure, they want to calculate the deformed geometry, which is the zero pressure geometry. So what does it look like when there's no pressure on it? So you can go ahead and calculate that. It's pretty neat. So you can see that the diameter increases. You can see all the deflections in here, and that's a fairly sophisticated analysis. And you can do that when there is large deflection, the diameter increases significantly when you put the pressure in there. So the next thing, again, another one of these really cool animations here is the ability to do pure displacement formulation for the linear TET solid 285. So most of the time, we're not using linear TETs, we're using TETs with mid-side nodes, right? But sometimes you want to have a more efficient solution. So and there's not a lot of bending, so you don't need that additional node. So let's go ahead and turn it off. And you can do this pure displacement formulation. Again, it's applicable, as it says in there, when you don't have a lot of bending or a lot of and it's incompressible. So it's a fairly rigid object, and you want it to run fast. And so this is a good example, this particular model here of a twisty bit. So that's a fairly significant deformation, but it works really well. Not a lot of bending. So the next thing is kind of an interesting capability, which is the general distributed load for solids and shells. And there's this new command called SF control, and it allows you to specify loads on a line or a surface. So a line on a shell or a surface on a solid. And it supports all current technology. So you can see the numbers here. So all the 180s, 190s, 285 for both 3D, 2D, 3D, 2D shells, and 3D, 2D coupled field elements as well. And why do we care about this? Well, you're applying the load onto the geometry of the elements directly and not using the surface effect elements anymore. So in the past, right, we would have to put a fake mesh on here using the surface effect elements and put those on and then apply our loads to the surface effect elements. Well, we don't have to do that anymore. We just need to get in there and apply it directly on there using this capability. So also, we've got enhanced 2D thermal elements for plane 292 and 293. And these are really great for very complicated thermal problems. And it handles the nonlinear thermal load with by really linearizing the stiffness, the element stiffness. And it does support the user MAPDL Fortran subroutine. So you can do your own subroutines for these as well. So just basically increasing our capability with 2D thermal capability. And you can see all the different, the 292 is here, which is basically a 4-noded one, and then the mid-side nodes, and it can be a triangle if you'd like. Now, speaking of user programmable features, we can now do user-defined material models for the 22X coupled field analysis elements. So the 226 and 227, and they support both the user mat and the user mat for the thermal, for structural and thermal capabilities. And we won't really get into the details of this, but you basically have to go tell it that you're going to be using a user-defined element, whether it's going to be nonlinear, linear, or mixed UP, and same with the thermal as well. And the primary application they added this for is the ability to do manufacturing process simulations. You've got some weird process that's, I don't know, removing material based upon some shear load or something, I don't know. And you can go ahead and put that in there and program that up. So that's it for the new elements. So they were busy there. Let's talk about contact, which is probably the most important, I think the one that's going to impact the most people of what's coming out in this current version, or is out now actually. So in the past, if you defined a preload and a fastener undergoing large rotation, it didn't really work right because the coordinate system shifted right and the direction stayed where it was. So if you use the MPC 184 joint element for doing preloads, You can now define the preload. You can define a force, a torque, and a rotation as well. And you can see the examples below where it's actually working with a large rotation. So that's kind of a big deal. That was a limitation that we had for some time, and that's now available. Oh, there's an animation here, so you can kind of see it. There it goes rotating. So they put the preload on, and then it rotates, and it doesn't get all funky. In the past, when it rotated, all those contours would change, but the pretension stays the same as it rotates. And here's some more examples. So pretty cool. And you can see here the stress, the old technique here, the stress changing as it rotated. So this is kind of another thing to make contact more robust, and it's called the fit modeling technique. And it's for I'm trying to think of the best way to describe this. It's for modeling the normal and tangential stiffness and friction in a ramped way. So instead of saying, you know, this is the value, as soon as you get contact, the value starts being applied, you can ramp it up over a load step or a time period that you specify. So you can increase the stiffness and increase the coefficient of friction over time. You don't have to have initial contact, which is another nice capability of it. So I think that's a key thing, and you can, it just basically makes it more robust, right? So here's just a spring going down, these plate springs moving up and down. So you can see as it pushes down, it's handling that contact fairly well. This is kind of a crazy thing. It's kind of, the animation's a little fast, but you can see it kind of goes up on the other side and then raises up, a hooked spring. And then this is a radial shaft seal spring on a circular spring. And I actually modeled one of these a long, long time ago. This was Teflon, and we basically had to do this manually because this was a relatively soft material relative to this material. And so I had to up the stiffness to manually do the converge. And we don't have to do that anymore. So we'll go to the next page. And then another thing is this capability to do exponential pressure for penetrating relationships. So, you know, generally it's a linear relationship, right? You go in 1/10 of an inch and it times the stiffness, and that's the force that you get back, F equals kx. Well, now you can specify an exponential curve for that. I won't get into the details of it, but in large assemblies, it seems to really help get things to converge faster. Another thing is a tangential pressure fluid penetration load. So this is part of contact. If you're not aware of it, Ansys has the capability to model whether liquid basically gets in between two parts and flows between those two parts. And you use the contact 172, 174, and target 169, 170. And those both now support tangential fluid pressure penetration loads. I always struggle with that one, fluid pressure penetration loads. In the past, you could only do normal loads, but now it's basically that shear load as the penetration is taking place. So if you've got a relatively viscous material between two plates, and you've got relative motion between the two plates, you can now calculate what that load transfer is between the two of them. It's a pretty cool capability if you need it. This gets really into the weeds, but it's kind of important. The biggie is that we've got a lot more checks to see if things are converging. Really, we almost do a whole talk on this whole thing. the primary usage, I'm trying to simplify it and not just read the slide, but the primary usage of it is when you've got problems that are never going to converge, or problems that are converged with the wrong solution, you now have this convergence reference logic to kind of help you get there without getting in and changing things yourself. So they give an example here where the automatic force convergence is too low and it's just never going to converge. It's just going to keep iterating back and forth. And then it automatically looks at it using this new logic and goes, hey, wait a second. This criteria is way too low. Go ahead and set it to 1, and boom, it goes ahead and converges fairly quickly. So I recommend that if you're having convergence problems, you take a look at these things and call your tech support provider. They can get pretty powerful to get us to converge faster, which is often for many of our users the thing that they struggle with the most is getting their contacts to converge. That's it for contact. Let's dig into the solver, the APDL solver. If you don't know what APDL stands for, it stands for Ansys Parametric Design Language. And that is the scripting language that the Ansys program uses internally. It's what we used to use to write all of our scripts and everything, and you still use it when you submit a job for mechanical into MAPDL. It actually creates an APDL script and sends it. So a little bit of history there if you care. What's in the APDL solver? So this is the actual solver. This is the thing that takes what you specify in mechanical or in MAPDL and the preprocessors, turns it into a solve. Really kind of an important one is the rcopy argument for distributed Ansys. So when you're doing distributed Ansys and you're moving files around on the remote machines, you can go ahead and use that command, which is good. It's like RCP instead of SCP because the default is SCP. And if you don't have SCP turned on, if you don't know what I'm talking about, your IT person would, but there are two different ways of moving files around, and you sometimes can only use RCP or rcopy. They've added logic to detect if the sig kill or sig abort ABRT signals have been made, and provide relevant messages to the user. These are ways for you to tell, hey, stop my run. So they've improved that. And then they always do in every release is improve the scaling. So they reduce the memory. Sorry about the doorbell in the back. We're all working at home. They've improved the block Lancho scaling, faster performance for fracture, and faster performance for the sparse solver when running out of core. And we'll talk about each of these things. So the reduced use of memory. This is their BGA model. It's a big monster model, 16 million degrees of freedom sparse solver. You can see that between R1, 2019 R1, 2020 R1, they've gone ahead and really reduced the memory usage quite a bit as you increase the number of cores. So you get a big advantage as you go up in the number of cores. So that's pretty significant. Our exterminator is here, so I apologize for the dogs as well, barking at the exterminator. You can hear that. So here's another example. This is a 10 million degree of freedom problem and getting bigger improvement on those large number of cores. So this is really only going to help when you're running on a ton of cores. I mean, even on 32, you get a little bit of improvement, which may be enough to fit on your machine. But as you go up in the running on clusters, it makes a huge difference. And this is money here. Why do you care? That's where you start charging a lot when you're running in the cloud, is when you start adding a lot of memory to the cores. So if you were on a machine with less memory per core, now you're talking. And then the same thing with the big monster engine block, even bigger increase again, improvement again. And the ECU is the last one, so pretty cool. Okay, so improved scaling, right? This is the same model here, so it confused me for a second here. This is the ECU model, the engine control unit model. It's 9.7 million degrees of freedom. Block Lancho's eigensolver. So you can see down here, the blue one is R19, And it actually started slowing down when you started adding cores, so that's not good. So in 2019, which remember 19 and 2019 aren't the same thing. This is a different version. They kind of fixed that. You still get a little bit of a slowdown if you go up to a lot of cores, but we're still getting some improvement there. A big improvement in speed up, right? And then when we look at the current release, 2020 R1, we got a nice chunky 3x speed up on 256 cores, and it doesn't slow down to go to 512. Well, yes, you don't get a big difference in speed here, but what if your model can't run on a smaller, you can fit it on a big machine now, and you don't pay a penalty for running on a big machine. So pretty cool. Most of us are living down in this world down here, and we're seeing some nice speed up there as well. So this can make a big difference, especially if you're doing a lot of iterations. Even 128 cores, it's pretty nice. Oh, they have a little animation. Increased performance over time. The fracture parameter calculations have improved. So this is a relatively small model, but what we're doing